This video is to improve the knowledge and understanding of methods of calculations, inverse operations, logical reasoning, percentages, conditions of congruency, and misrepresentation of data. The method is called Spot the Mistake, and it's how learners can learn from each other's mistakes in a safe environment. Presented by Tony Bearden, Barry Barnard, and Caroline Ainsley. This is one of the really powerful methods to, number one, identify the misconceptions and then together help the learners work it out. Now, with AIMSEC and the Global Teacher Empowerment Network, we use something called spiral learning, or the learning spiral. So the idea is this is a lifelong learning spiral, and it starts when you first start learning, when you're a little baby, when you first start hearing, experiencing the world. And so we've got the logical reasoning that we all have at the beginning, and every activity we do includes a logical reasoning activity. So it's something that everyone can have a go at. And then with the spiral learning, you have it progresses up through the early years. In lower primary, you can literally do spot the mistake lessons. And then upper primary, you keep going up with looking at the misconceptions that have come in by then. Mistakes with mathematical notation, mistakes with language, misconceptions of the words that are used in mathematics that are different to English. There's some specific things like percentages, fractions, the difference between 2 times a number or the number squared, things like that. And then we've got real life applications like representation of sales figures. We've got misunderstanding of data, misrepresentation of data, misunderstanding of statistics. And then moving on up, you're now really using mathematics in a very practical way, modeling, problem solving, and using and applying mathematics. So that goes from upper secondary all the way through. Mathematicians are in high demand in industry. This is the concept. It's about making mistakes. It's about how you respond to making mistakes. This poster is so wonderful. Making mistakes isn't a time to go, no, I made a mistake. I'll never get good. I'll always be rubbish. I'm stupid. So many of us think that way. That this poster, this one, everyone needs to have up in their classroom. A classroom should be a mistake-making, laughter sharing. Mistakes can cause laughter instead of despair. Mistakes can help build independent thinking. Mistakes can stretch your brain. Mistakes can open your mind. Mistakes can make you realize things that you never ever realized before. And well, this classroom, every classroom is definitely the sort of place where everyone matters. I absolutely love this poster. Tony's my helper when I'm on stage. Tony and I have this little thing we do, and I say, I've usually made a mistake prior to that, and I'll say, I never make mistakes.
And Caroline always tells the truth, believe me.
And of course the audience say, of course you did, you just made a mistake. And I say, I haven't made a mistake. I made a magnificent mistake.
Or you had a good learning experience.
I had a good learning experience. And the reason why I convert it from something which can make you feel sad or bad about yourself into something good, I use one very solid tool. That tool is to ask myself, what did I learn? And I use that in real life all the time. What did I learn? And that literally transforms you from an experience where you've had a bad experience and you feel bad about yourself to, well, what did I learn? Oh, that lifts you up straight away, and it looks at and it finds the learning rather than the bad feeling.
And it's natural to people to make mistakes and learn from them. Babies fall over hundreds of times while they're trying to learn to walk before they actually are steady on their feet, and they don't give up, and they don't get upset about falling over usually. Yeah, so it's when they go to school quite often, sometimes before they go to school, and people tell them to be quiet and stop asking questions, but children are naturally inquisitive, and if teachers seem cross when they make mistakes, or friends and other children make fun of them because they made a mistake, then School becomes not a place for learning, not a place for eagerness about learning, but quite the opposite. So the next thing is to think about logic, and everything we do in maths involves logical reasoning. So we've just got some simple arguments today to look at. And at this stage, we're doing something that you could do with young children as well as adults and everything in between. So my question now is, are these arguments valid or invalid? And we'll take them one by one. Now, the first one is, if Layla went to a party, then she wore a red skirt. Now that we take to be true. If she went to a party, then she wore a red skirt. Now, does it necessarily follow that Layla wore a red skirt, therefore she went to a party? So in the sort of mathematical notation, we say if A, then B, and A is Layla going to the party, and B is about the red skirt, and that equal sign with an arrow on it, that means implies. So if A is true, then B is true, is what that symbol means. Okay, so we've got a little bit of logical notation here. And now here's a picture, the party, everybody, those girls are all dancing, and there's a Layla in a red skirt. So we're taking it, she went to a party and she wore a red skirt, but she could have worn that skirt and be doing something completely different. There's a picture of her walking in the woods there reading a book. So she's not wearing the red, she's not at the party, she's in the woods. So that little tilde symbol means she's not at the party, but she is wearing the red skirt. So that's argument is not valid. The rest of these situations, just write in number 2 valid or number 2 invalid, whichever you think. Now, number 2 is this: if she's my sister, then she's younger than I am. She is my sister, therefore she is younger than I am. Now, it happens that both Caroline and I have got sisters, and we don't have any older sisters, we have younger sisters. So that would be true for me. If she is my sister, then she's younger than I am. And if that person there is my sister, therefore she is younger than I am. So is this valid or invalid? Okay, she is my sister. That person over there is my sister, therefore she's younger than I am. You don't believe it? It is valid. Okay. If she's my sister, I've only got younger sister, I don't have any older sisters. The next one, if she's my sister, then she's younger than I am. Same first statement there, okay? That person over there is not younger than I am, therefore she's not my sister. Is that valid or invalid? So Pam, you could decide on that. If she is my sister, then she is younger than I am. That is certainly true. Is it true that if she's not younger than I am, then she's not my sister? That's a valid argument again. And notice there, it's not younger is a little tilde before the B, and not my sister is a little tilde before the A, a little twiggly sign in the air. Okay. So both of those statements or pairs of statements involving something about sister, they're both valid. And now what about this second one about Layla? If Layla went to a party, then she wore a red skirt, same as number 1. But the conclusion here is Layla did not go to a party. Therefore, she did not wear a red skirt. Is that valid or invalid? Well, actually, just because she's not at the party doesn't stop her wearing the red skirt. So that's not a valid argument. So the arguments on this page about Layla and her skirt and the party, they're all invalid arguments. Whereas the arguments about the sisters and being younger, they're both valid. Now, this is truly very important, because not only does it affect all the maths we do, that we can, we're clear about what we're assuming to be true and what follows and what we can prove, but also it underpins the whole way computers are designed. It underpins all of computer programming. These circuits, these logic circuits, are built on is quite a lot more complicated than we've made out this afternoon. It's quite a it's not all that complicated, I have to say, but there are things like truth tables and networks, logic networks, and it's what's behind the way computers are constructed. So logic is extremely important, but also quite apart from anything to do with computers and mathematics, it's how we conduct our lives. We have discussions with people. I'm not saying that we have conflicts and arguments that are, we get cross, not at all, but we do have discussions with people in which we make a case for something that may be having nothing to do with anything to do with science, but it's nevertheless part of life that we have these discussions, and sometimes they're logical and sometimes they're not.
Lawyers and politicians, anywhere whether the debate about the climate, it's all logic, and it's all if it has to be well analyzed.
Yes, indeed. And politicians want us to believe that they're the best party, so they try and convince us, and their logic isn't always valid.
And it's important to be able to spot the logic that is invalid. So it's a very important life skill.
Absolutely. Now here's some simple examples.
Here's another one where we apply a bit of maths. Statement A says if x is 5, then x squared must be 25. So the if-then statement is if A, then B. In maths terms, if x is 5, then x squared is 25. So I think we agree with that statement. But the question now is, does the converse hold true? And I think that's coming up now. So it's true that B implies A. And here we have a good look, and we see that minus 5 squared is also 25. So a minus 5 could also be an answer for x. So that's the converse in this case is not true. It's not the only answer that we can get. So let me just go back to this full screen. Yeah. So then if the statement on the right-hand side says there's a number, the number is 0, and then statement B says if we add this number to itself and we multiply it with itself, then we get the same answer. Is that true? And we get 0 plus 0 is 0, which is equal to 0 times 0, and then it's also the answer 0. So now, if you get a 0 answer, will you get the A eventually? Or if you take the converse of that, and here we can think of one counter example, or because the number that you can work with is say 4, which you can get if you add 2 plus 2 and if you multiply 2 times 2. So the converse is not true. Just because something is true, its converse is not true. Well, we can't assume that it's true. It's got to be proven true.
Mm-hmm. And it's also important, isn't it, that people recognize what they're actually doing, whether they're using a theorem or the converse of a theorem. For example, you have to prove the converse of Pythagoras' theorem. It isn't necessarily true just because Pythagoras' theorem is true, but actually it happens that the converse is true. But we should, as teachers, be helping our learners to appreciate the difference between one reasoning, which is an argument, and the converse of that argument.
For children to learn to think logically, that automatically happens when they're very, very young. But we can help encourage them to actually reason logically, apart from if they just want some chocolate or they want to stay longer before bedtime or not brush their teeth or whatever. They're really good at arguments like that, but they're not necessarily logical arguments. So we want to help train them to become better at logical arguments. We might have a few more satisfying moments that way. So the question Tony's come up with some great questions that we can ask younger learners. So when it rains, we stay indoors. Well, does that also mean that we are staying indoors, therefore it must be raining? You can have that conversation with a young child, and you can even do it on a day when it isn't raining and say, well, are we indoors? Is it raining? So that argument is very visual and very easy to demonstrate, to
They might be
real.
indoors doing something that's really important to them, playing a game or having their lunch or something.
There might be asleep.
Exactly. And it doesn't mean it's necessarily raining just because they're indoors, and they'll appreciate that. So it's an invalid argument. However, there's lots of arguments that Caroline's going to talk about, which children will come up with themselves, won't they?
So there you go. When mummy comes home, she puts me to bed. And they will come up with the argument of, I don't need to go to bed because mummy's not home yet, so I can stay up late. My mummy says it's okay for me to stay up until she comes home. And they will have a go at that with the babysitter. And that is most certainly an invalid argument, because mummy might be home late, especially if there's a babysitter. And then last time we went to Granny's house, we had chocolate cake. So can you assume that you're going to Granny's house, therefore you'll have chocolate cake? Well, actually, it's possible. If I went to my Granny's house, there was always fruit cake, always. So we knew there'd be fruit cake at Granny's house, but maybe on some occasions there weren't. So it's not an absolute, and it's not a foregone conclusion.
Most grannies will try to please their grandchildren, but on the other hand, Granny may have been very busy, so she might not have had time to make or get the chocolate cake, so she might have some other treat in store, you know.
Now, actually, it was Dundee cake with my grandma, and also, now here is one. I didn't like the taste of cheese when I was 2. That this very sensitive subject of food. So is it logical to think that they might not like the taste? I'm not going to like the taste of food now that I'm 5. Well, thank goodness it is actually true in this case. And a child will acknowledge. My grandson has commented very recently. He says, oh, I didn't actually like apples when I was little, but I do like them now. So it does change. And that is something that is not... it's invalid, and it's not an argument. It's not an argument they can use to say, I didn't like it when I tasted it when I was 2, therefore I'm not going to like it when I taste it now. A very emotive argument there.
But it can be an argument for them refusing food, and it actually, they probably will stick to their guns for quite a long time if they're determined.
Logic has nothing to do with it. But it is a great, you can find lots of examples, and come back and type in the comments if you come back to this video later of examples that you can think of, or actual real life examples you've encountered to help others.
We'd love other people to share their ideas here, and if they if the discussion arises in class, and it's a simply not a logical argument, but this child is very convinced they want to convince other people, then it's something you might want to have a class discussion about.
Well, this slide is what we actually want teachers to do, to create an atmosphere in their class that everyone believes that mistakes are good for learning experiences. So this poster, we've seen it earlier today, and it's actually what AIMSEC stands for and want teachers to do in their own classrooms, and to work with mistakes and to make notes of mental or written notes of when learners make mistakes in mathematics, and then frequently write them on the board, or give a few incorrect examples on the board and ask the learners to work in pairs and to spot the mistake, and then also to explain why it is a mistake and how it can be rectified. So this is a powerful way of working in your class, and make it so the learners are not nasty to one another if a mistake is made, but ask what can we learn from this? So it's so important. So I think this slide demonstrates that, and the whole idea of spot the mistake, the whole afternoon is dedicated to things like this. There's the first one coming up. I think that one was...
Tony, this is yours.
Okay. So here's some arithmetic. Now this slide is here to show different methods, and what we would do, how we would use this is to write these methods up or give them in a worksheet and ask the learners to explain the methods and how they work and find the mistakes, or maybe there's just one, and put it right. Give them some time to do that, perhaps on their own, and then maybe to discuss it with a partner. And what do they actually see here? Well, we worked on this rectangle, an area for multiplication, last time, didn't we? Do you remember the treasure chest when we were sharing this treasure between 8 people? And here we're multiplying by 8 and also dividing by 8. And what do we notice about that? So there's a great wealth of number sense and number ideas in this slide, in this one slide. So we're only involved with this area method in actually multiplying single digits together, because when we multiply 8 times 70, we need to know is 8 7s are 56, and that's in the 10, that's 10, so it's 560, and 8 9s are 72, and so 8 times 79, we add up 560 and 72, and we get 632 as the answer. Now, when we're going to divide, if we're going the opposite way, and we start with the 632, and we're dividing by 8, then, of course, we can set it out as below on the left. That's what we call an algorithm, and that's a pattern that teachers often teach the children to use when they're doing division. But another way to do division is chunking. And by chunking, I mean actually to, first of all, out of the 632, subtract 80s until you get down to something that's smaller than 80. And so you can actually subtract 87 times, and then you're left with 72, and then you have to subtract 8s. So you ask how many 80s and how many 8s, and you break your 632 into 80s and 8s. You might have a remainder, but you haven't this time. And you get the answer is 560 divided by 8, which is 70, and 72 divided by 8, which is 9, and gives you the answer 79. The mistake is up on the...
Oh, hold on. Let's see if we can find the mistake.
There isn't a mistake. Oh,
there
yes.
Is a mistake.
There is a mistake.
So with each of these slides, as soon as you see the slide, but please start spotting the mistake. Have a look and see if you can find the mistakes. There is it only one mistake on each slide, Tony?
This one, well, you got to look, but this one has only got one.
There might be more than one. This one only has one. Okay. So spot the mistake. Let us know where it is.
Well, I think everybody's convinced, at least I hope they are, that 79 times 8 is 632. And so how did they get 642 there? Well, they probably got 8 9s are 72, but so they should be putting down 2 and carrying, if you like. That language keeps coming up. But then they failed to get that correct and got 642 rather than 632.
Yeah, we've got 2 responses in the chat. Say the mistake is on the left, where 8 times 79 is 632. And then Pam said the mistake is also on the left-hand side.
Here's another one.
We're looking at, again, different methods that work. So that's the beauty of looking at the mistakes in this way, is that everybody gets to have a go and experience the different ways of doing it. So this time it's division. Or we've got, well, no, it's the division is included. That's just checking this, isn't it? So where is the mistake here? What we're looking to really get solid on this is the inverse operations. And with very young learners, a really nice way of doing it.
The mistake very often occurs with applying the algorithm that the children have been taught, because they're not thoroughly understanding everything about the algorithm. They just have to make sure they get everything lined up in the right place, and because that's the way the teacher wants them to do it. So in some lessons, I hope it's not yours, because children have their own method of doing a calculation, and it can be quite efficient. Or if it's inefficient, then they need to be helped to, you know, be a bit more efficient. But it's the division algorithm here that's wrong, isn't it? And they start off all very well, and they get 230 something, but then they divide 63 by 7, and I think it's their the knowledge of their multiplication facts that lets them down there. Caroline's talked about inverse operations, and we quite quickly with children understand that if you want to undo an addition, you subtract what you've just added and you get back to where you started. And similarly with multiplication. But the shoes and socks together give you 2 operations, and this is laying the mathematical foundations for functions and a lot of work that comes later on, and is very important. So if you just take here 5 times 2 add 3. So you do that because you do the multiplication first. You've got 10 add 3 and you get 13. Now, if you want to undo that, if you take the 13 and divide by 2 first, then you get 6.5. And if you subtract 3, you don't get 5 as your answer. So if you start with 13 and do that, you don't get back to 5. So actually you have to do the operations in the opposite order, as well as doing subtraction to undo addition and division to undo, which is the inverse of multiplication. You've also got to do them in the opposite order.
Just like with the shoes and socks. Pam loves the shoes and socks analogy, and she uses it. Pam always uses the shoes and socks analogy when teaching solving 2-step equations. Brilliant.
It applies to equations, it applies to functions, and it's really a useful idea. But it can be an idea that children meet in primary school, and it's not a difficult idea.
Yeah, so this is the third puzzle of where we have to spot the mistake.
Well, here again, you've got the area method of multiplication.
The table works always well. But I think on the left-hand side, the person tried to do the 5, multiply by 5 first, and then getting the 145, but it should come later, so the digits are not in the right position. So I think that's where the operation goes to.
Well, they're multiplying by 5 rather than 50, aren't they? And then they're multiplying by 10 and not 1, and so they've completely misapplied the algorithm there.
Pam says they forgot to respect the position of the digits and multiply by 10, not 1. And also, and this is the beauty of this activity, that there can be discussion about what's happened and how it's happened, and the learners themselves can have that discussion like we're having. 3 people are saying something slightly different, all saying everything's correct. That 3 different ways of approaching it, and that's so powerful for the learners to actually have that discussion about it.
Also, the one on the left bottom, where you have the 29 times 51, and then you round off. Instead of taking 29, you take 30, but then you must remember to take one of the 51s away again. So I like that method, and you get the same answer. On the right bottom side, Tony.
Actually, it happens that both these numbers are near just one different from a multiple of 10. So that gives us a method that we can use. That means that we can do this by mental arithmetic and get the right answer. So, so instead of multiplying 29 by 51, well, we are going to do that, but we're going to multiply it by 50 first, and then add another 29 because we're supposed to be multiplying it by 51. And then when we're multiplying by 50, it's a good idea to multiply easy to multiply by 100. So we double the 50 and to get 100, but then we'll have to divide by 2 as well.
There must just be a decimal after 14.5 or 14,5 to get 29, and then multiplied by 100, then you add the 0 again.
Okay, I should have had a I should have had a point in there.
Yeah.
So there's another mistake. You found the mistake. It's nobody spotted that
It's
one.
perfect.
Until,
No,
Barry, until Barry spotted it. Well done, Barry.
But yes, but it's a mistake, and this is a perfectly valid place to have it.
Yeah, absolutely.
You still got the answer right. See, this is also a very good example, because you can make a mistake along the way and still get the answer right because you've done it all in your head, but you've written it down wrong.
Yeah, and this slide should probably say spot the mistakes because there's more than one.
It does. It says spot the mistake. Oh, the top bit says spot the mistake.
Yeah, it does.
Yes.
It does indeed.
It does.
Yeah. Here's the last one. This is number 4. Again, we've got multiplying by hundreds, tens, and units. Same method. This time it's 34 by 129. And where's the mistake here? Where's the mistake? 129 by 34. So we've got 100 times 30 is 3,000. 30 times 20 is 600. 9 times 30 is 270. And if we add those up, we certainly get 3,870. Is the bottom line right? And is 4,386 the right answer? That looks okay. So again, it must be the algorithm that's wrong on the left. So
there was somebody in the chat just now said that 129 times 4 is 516.
Okay.
Yeah, I'm just, yeah.
So it's the 486 they've got wrong there. And again, they've got 4 9s are 36, and they've not carried that 3. They've just said 4 12s are 48, haven't they? I think that seems likely. And what we've got written here is doing quick, accurate calculations is for calculators and computers, not for people. I mean, in this world, you may want the children to learn calculation methods, but it's much more important that they understand the methods than anything else. And they can estimate the calculations so that when they use a calculating device, they know if there's a big mistake. And usually the mistakes are not like so small you wouldn't see the difference. Very often you can pick up your mistakes by doing an estimate. And in this world, as I say, using the tools is what we need mathematicians to be able to do.
This is an example of how understanding percentages really matters. And there's so many areas where this applies to real life. Now, Tony actually told me the other day, I didn't realize our government has just done exactly this. They cut funding by, let's say, by 10% 10 years, more than 10 years ago. And now they've increased the funding, let's say by 11%. But the question is, when you add 11% to 90% of the original, do you have more, less, or the same as you had in the first place? So you think, take away 10% and add 10% of what was left, might logically sound as though it might be the same, but is it? And this is where understanding this is so important. And this happens when people get pay cuts and then they get a little bit added again, and you think, oh, I'm back to where I was. Were you? Or if prices are manipulated in the high street and they talk about percentages. Pam comment on the previous one is that she always asks them to write down their workings out method down, even if they do it mentally, so that if there are any mistakes, they can be spotted. And now Pam is saying it's not the same, as it's 11% of a smaller amount.
The answer is, how much would the funding be at that stage? And it's going to be increased by 11%. It's going to be less than $1 million.
It's less than $1 million, basically, yeah. So it sounds as though 11% added is going to be more than the 10% taken away, and it's not. Other examples of this one is playing with percentages, and this is often not done deliberately. I'm not saying the government doesn't know better, but somebody who owns a little shop perhaps might make these mistakes completely accidentally because they don't fully understand percentages. So it's up to you to know, so that you're not hoodwinked by someone, even if it's accidental.
This is very common, though. They arise because people are talking about percentages, but they're not saying what this figure is a percentage of. It's the base. What is it a percentage? What you're telling me, what is it a percentage of? And that is the ambiguity there. Is it the percentage of this figure, or is it a percentage of some other figure? And that's where the ambiguities arise, or misrepresentations of the truth, or, then what they say may be true, but they know very well in the first case that the majority of voters won't recognize that there's now less funding than there was in the beginning.
Yeah, it's increased by 11%. Obviously, there's more funding. The sentence is incomplete if you just say it's 10%. 10% of what is absolutely critical.
The idea is for things like the Black Friday sale, big sales, to make people think that they are getting a real bargain. Well, they are actually, it's a sale. They're getting some sort of a reduction, but it's not as much as they're being led to think.
Because the prices can be increased prior to the sale. So they're increasing the prices and then making a huge reduction, but it's based on the highest price they had over the last year. And that was at some point placed artificially high so that the sale could be genuine and yet manipulated. And so do not be hoodwinked. Don't be manipulated. Know your percentages.
We've been moving gradually up through the school years, and we've moved into the phase for lower secondary. So we're really talking about 11 to 16-year-olds now, and the sort of things that they can understand and meet several times so that they gradually become more proficient with these ideas.
We're in the lower secondary and we want you to spot the mistake, but I'd first like you to try and make the drawing that satisfies the information given. And what would that angle look like? You can first try it yourself.
Are all the angles acute?
The angle must be 50, but it must be angle BAC, not ABC. And then the degrees at angle A is 50 given, but then the side BC is 5, which is shorter than the 6. So it can either go this direction or the other direction that's shown now. If the side opposite the angle is smaller than the other side, then you usually get these two cases.
Pam has said that is the ambiguous case. Pam is well clued up.
BC on the right-hand side will give a triangle. It's all acute angles. So ambiguous case. Pam, thanks for that.
Yeah, so ABC1 has got an obtuse angle and ABC2 has got all acute angles. I agree with Pam. We're getting into a bit of physics, but very much an everyday life example here.
And I do love this because there are some great questions. This is a bit like the percentage of what. So have a look at that. The cup of coffee started at the 63 Celsius. It was quite a cold cup of coffee already. And we measured the temperature. After 3 minutes, it had gone down to 54 Celsius. And so we're extrapolating that. So I used the information to draw a graph, extrapolated from that information, and there's the graph. The question on there is, what do you notice about the graph? Comparing it with real life situations, what might the learners notice about it? Some learners might be perfectly happy with that graph, in which case it would be very useful to have input from all the learners in the class to have a good discussion about it. What is wrong with this picture? If I'm in the Antarctica and it's July, it might be -40. So it might actually become a lot colder than that a lot quicker.
Well, I think you are in the Antarctic, actually, if this graph is anything like to go by, because
I have to be in the Antarctic.
no, you're not just in the Antarctic, you're actually in the freezer.
In a very cold freezer. We can now derive from the new graph at the bottom what the room temperature is.
I don't think it really matters. I mean, the point is that interpolation is quite a reasonable technique in mathematics. Here we see that for the first 3 minutes, there was certainly a linear relationship, and certainly to the nearest degree at least, the temperature cooled down 3 degrees each minute for the first 3 minutes. So if you were asked, what would a cup of coffee be? What would the temperature have been after 1.5 minutes or 2.5 minutes? You could have made a reasonable reading from the graph and got a reasonable answer. But you're not justified in extrapolating there, because just because you start off with a linear relationship, you cannot assume that the relationship will go on to be linear. And in fact, a cooling curve looks something like the graph on the bottom of the left-hand corner of this page. And
I think it's a very powerful way to introduce that in a physics lesson or science lesson, to start with that linear and say, right, here it is, what do you think? And then just to discover the experiment where we actually started with a certain temperature and we drew our own graphs. And I was very surprised, and I haven't forgotten it.
It was originally called Newton's law of cooling, but it has been refined with acute instruments. There is a cooling curve that looks something like that. And physics says that the rate of cooling depends on the difference from room temperature. A cup of coffee won't cool to less than room temperature. It's an example in real life as well of that being a horizontal asymptote there. We're still in lower secondary.
Yeah, and we're doing this one now. Mzu, we worked out 4 to the power 3 to the power 2, got an answer. Najwa did the same, and she got a different answer. Who is right?
I actually did this. I actually went and had Leon have a look at this.
He's 13, is he 14?
He's 14.
Yeah.
And he came up with 4,096, so that was good. But then when I wanted him to consider the other possibility, he was completely confused. And then after a bit, he was like, well, it worked out. First of all, I asked him to estimate what he thought it would be. And he thought it would be, it's going to be about the same. He decided it would also be 4,096. So it was a nice surprise for him to discover it was very different. And hopefully that will help him remember that there is a difference between them.
How you interpret the powers. That's in the first case, in Mzu's case, that's 4 to the power 3 that he did first, got 64, and then squared that. And the Najwa worked out that first the power is 3 to the power 2 got 9, and then it's 4 to the power 9, which is a much bigger number. So we should actually be careful when we ask questions like that in Olympiads or even in class tests to actually put the brackets in the right positions, like at the bottom two rows. It can be confusing if you don't have the brackets there.
Well, it is ambiguous again, isn't it?
Yes,
It isn't clearly defined. So uniquely defined doesn't mean anything.
Temba says nobody is correct since the question is wrongly set.
But I don't agree with Temba either. I think it's the person who wrote this down in the first place. In other words, the teacher who was wrong here. You should not have, whoever gave this to Mzu and Najwa was wrong, because it isn't correct mathematical notation.
My view is that they're both correct.
I think they're both correct.
Made assumptions, but what they didn't do is state their assumptions.
What the test of this is, you couldn't type that into a computer. It wouldn't know what to do. You'd actually have to, if you tried to, or a calculator, you'd actually have to, in effect, you do one operation before the other, either do the 4 cubed operation before you squared it, or do the 3 squared operation before you took that power of 4. You'd have to know which keys to press and what order in order to get an answer at all. So now to move on to upper secondary, we're going to think about some situations where we get percentage paradoxes again and other things that go wrong, or we can be quite sure of something and actually be wrong. Okay, so consider the situation where there's a couple of basketball games and you and your friend are both keen on basketball, both playing the games. And on Saturday, you got 7 goals out of 8 attempts, which was pretty good. But your friend got 2 goals and he'd only tried 2 shots at goal. And so your rating was 7 out of 8, which was 87.5%. And his rating, your friend's rating, was 100%. So your friend did better than you on Saturday. And then on Sunday, you scored 1 goal from 2 attempts. And your friend was, it was a girl playing basketball. She scored 5 out of 8. So her rating of 5/8 or 62.5% was better than yours of 1 goal out of 2 attempts, or a 50% rating. So again, your friend scored at a higher rate than you did on each of the 2 days. Now, does that mean that your friend has a higher rating when the 2 days are combined, when the figures for the 2 days are combined? Work it out. How many goals did you score over the weekend, and what was your rate of scoring? And how many did your friend score? And who did best overall when you take the whole weekend into account? I think what may have happened is that you got a surprise here and it didn't turn out as you expected. It's what's called Simpsons Paradox. You scored 8 goals out of 10 over the weekend, so you got a rating of 80%. Your friend, she scored 7 goals out of 10, so she got a rating of 70%. So although on Saturday her rating was better than yours, and on Sunday her rating was better than yours, over the whole weekend you did better. Now, that is counterintuitive, I think.
It certainly is. I'm still struggling with it.
It shows that you have to be cautious when you're interpreting data and drawing conclusions. And very often when we're drawing conclusions, we draw the wrong conclusions. And now here, what happened is given in the table. And if you compare the table there with what's written above, you'll see it is exactly what's written above. You got 7 out of 8 on Saturday and 1 out of 2 on Sunday, altogether 8 out of 10. And your friend got 2 out of 2 on Saturday, 5 out of 8 on Sunday, altogether 7 out of 10. So she did better on both days separately, but you did better over the weekend taken as a whole. So that's strange.
We have drug trials and we've got some very clear data here. Intuitively, you look at the two, which one is going to come out as the winning drug? You've got look at anti-misanthropia. We've got 90% versus 80%, 80% versus 70%, 70% versus 60%, 60% versus 50%. Every single category, the percentage of misanthropia wins over anti-cynicismia. I like these names. Before you reveal, Tony, I would like to use an example that I use, which is I find is quite powerful, especially for people that aren't confident with percentages, apart from the fact that this is counterintuitive anyway. And that is that you get, the newspapers love to do it. There's been 100% increase in cases of, I don't know, broken toenails this year. But what they didn't tell you was that there was only 1 case last year. And this year, there were only 2 cases. So it sounds, and they've got this the lovely big percentage number, and they can run with it. Now, this isn't about that exactly, but the point is that the numbers matter. The amount of people we're looking at, if you now look more carefully, you'll actually anti-cynicism here. Look at the numbers. Look at, okay, so for the last one, group E, only 2 out of 5 people were cured. But for all the others, if you look, the total numbers, not
We've got to do a bit of arithmetic here.
Yes, you got to do a bit of arithmetic. The total numbers are the same, as you'll see in a moment. They're all out of 1,000. But for the anti-misanthropia, you'll see that they're only very, very small samples. And therefore, the end result is, even though the percentages were higher for misanthropia, anti-misanthropia, the anti-cynicismia actually had a better result. And that is definitely counterintuitive. Take me out of here, Scotty.
But it is very important because, you know, medical trials all are based on this sort of grouping. Usually there's more than one group involved, and usually, you know, they are comparing the number of people who were cured, and that's the success rate, the rate of, you know, the proportion of people who were, or percentage of people who were cured. And so this could be a proper medical trial, and doctors might well think that anti-misanthropia was the better drug, because every time it seems to have more cures. Okay, in each of those 5 groups, there are more cures, as Caroline has said. And yet, when you put them all together, it's actually the first drug, the anti-cynicismia, that's the better one. So it's again a question of beware how you use statistics and how you interpret statistics. The more
it should come with a warning label. Statistics should come with a warning label.
The more you actually know about statistics, the better, because it affects everybody's life, really, doesn't it, in some way or other? And just at the moment, it certainly does, with all these medical trials, because we, you know, a year ago, we didn't know very much. Nobody knew very much about COVID. Now there's been a lot of tests, and much more is known. And as a result of the tests, actually, that's how it's known.
But the thing is, it applies to politics. It applies to newspapers. Of any kind of campaign, whether it's a sales campaign or any kind of campaign, they will use statistics, and they will, and especially newspapers, they'll grab, you know, anytime it's a big statistic, 100, 200, 300%. And increase, or we're going to have a big thing, and that actually that somebody said somewhere that there might be a big storm next week, and the newspapers will go, hey, it's been said, we can promote it everywhere. And but they're not, that in that case, they won't mention the statistic of how likely it is to happen. And it's be aware. Check your facts.
So people responsible for interpreting data need to be aware of averaging percentages when the percentages relate to different totals, and that often gives this type of result. Now here, Barry is going to show you this on GeoGebra in a few minutes, but if we look at this graph here, we've got the same paradox. So we've got 2 journeys here. Red and blue go on a journey, and the gradients of the lines show different average speeds for different parts of the journey. Okay, so what you look at, if you look at the graph, you'll see OR1 is the first part of that journey. In the first R, the red goes 90 kilometers, and that's average speed of 90 kilometers per hour. And then there's the next 5 hours. He didn't go far because he stopped to visit a friend, and overall his progress, as it were, on his journey was only 50 kilometers, and over 5 hours that made an average speed of 10 kilometers an hour. And you can see that from the gradient of the graph. Now for blue, the first 2 hours, blue did 120 kilometers at 60 kilometers per hour. And then for the next 2 hours, he didn't go far, he stopped for lunch. And so his total journey is shown on as OB2. And red's total journey is shown as a dotted line, OR2. Now just look at those two journeys, the dotted lines, and compare those. Now, who on average overall have the greater speed? The greater speed is shown by the gradient of that straight line. Okay, so this again is an example of the same paradox, because although red was faster on both legs of the journey, red was faster than blue, when you take the journey as a whole, blue's average speed was working out 126 kilometers in 4 hours. So that was 31.5 kilometers per hour. Whereas red, he or she did 140 kilometers in 6 hours, and that was only 23.3 kilometers per hour. So isn't that strange? That's a paradox again. So red's average speed was higher than blue's on both legs of the journey, but red's overall average speed was lower than blue's. Now, we've seen this apply to the number of percentage of cures in a group in a medical test. We've seen it as in sport, and it can apply in lots of other contexts. So over to you, Barry.
Well, I'm a GeoGebra fan, so I tried to create something, and to me, the solution lies in the slope of the blue dotted line and the red dotted line. So I've now created GeoGebra, and I use that icon on the top line to measure the slopes. And there you can see, for instance, R2 to 0 has got 7 units over 7 units, which is 1. The gradient of that line is 1. And the blue dotted line is 6.5 over 5, which is 1,3. But now, to me, the slope of those two lines is the indication of which one is the better. So if I move the point R to any position, but the red dotted line is still below, the slope of the red dotted line is smaller than that of the blue dotted line. So then doesn't really matter where I put that one on that side. But as soon as I get to the same position or even higher up, then the red slope is better than or steeper than the blue one. So with that, I'm just demonstrating with GeoGebra the same idea. So I'm a fan of this free software, and one can use it effectively in the class. Then you can also start playing around with the first leg of but that doesn't really change the slope of the the blue dotted line. Okay, so when you want to go back, you can just press the return button and go back to your regional layout. So
that's really good, Barry. I like it. I like it a lot. And the thing about using GeoGebra is that this paradox occurs in many contexts when groups of data show a particular trend. And when this trend is reversed when the groups are combined together. But you can be your context, your practical situation can involve all sorts of different measures like percentages, ratios, gradients of line segments or speeds. Now, of course, the graph is showing whatever it is as a gradient, but it could be it could be speeds, but it could be other things like goal averages in a sports contest and all that sort of thing. So according to the context, then the labeling of the axes will be changing, won't it? Yes. And the beauty of what Barry is showing you is he's showing you that he can alter that GeoGebra graph to fit any context where Simpsons rule applies. with two, just with two groups. And of course, he could add more groups in as well but it was simple to show you. And actually, the beauty of GeoGebra is that it takes a little bit of time to get your mind around it, but it's quite quick to learn, isn't it, Barry?
Yes, the icons at the top is sort of self-explanatory. If you press one of them, then it drops down and you can pick what you want to do. So you don't have to remember all these things. It's there on display for you when you need it. And
there you see, not labeled, and it can quickly be changed to fit in with any context. And so I think the cautionary tale is, as before, that what we should do is treat statistics with respect and be very careful about the conclusions we draw from any statistics. Okay, and here we have got a story, another context. So I'm a salesman, and these are my sales figures for 5 years. And oh my goodness, my sales have dropped in the last quarter. So that the sales figures are given there every half year for the end of quarter 1 and 3. And in the last quarter, my sales have dropped, but I want a pay rise. What should I do? Oh, I want to go and talk to the boss and ask for a pay rise. What should I do?
Well, this will depend on how good your boss is at interpreting data. So what do you know about your boss? Is he one of those people that says, I was rubbish at maths when I was at school?
Well, I don't know.
In that case.
Well, I'm going to be entirely honest, because the worst thing I could do would be to show my boss how dishonest I was. So I have to be very honest. So I decide that I'm going to show the boss the cumulative sales graph and not the sales. Now look carefully at those cumulative sales. What does that look like? The sales are increasing.
The sales are increasing, and the sales are definitely greater in quarter 3 than they were at the beginning of 2013. No question. They're greater.
Well, even in that last quarter, there are some sales, but just notice that at the top right there, that the slope is less than it was in the previous quarter, which just shows the drop in sales. And so if my boss notices that, he'll ask about that last quarter. He might ask for the detailed figures for that last quarter. But like as not, he'll just look at the graph and say, oh, in the last 4 years, your sales have been going well. Isn't that great? And I'll get my rise.
So, gradients matter.
Yeah. Yes. And I think, again, this could be an example where you tell, not in this case, you're what they say, economical with the truth. You're not actually going to tell a lie now, but you're going to tell the story in a different way and hope that the person you're addressing it to will draw the conclusion you want him to draw.
A different perspective.
Yes.
The numbers have gone up.
Indeed. Now this is this next slide, believe it or not, is a genuine slide from Tim Cook from iPhone, from Apple.
Yes, Tony, and there on the right, top right, the same thing happened. So they actually not telling the truth here, but the sales of the phones have dropped, and that trend could extend further. But with that graph, it doesn't interfere so much with the detail. So our salesman, this person, Tim Cook, actually made Apple to be better than it was with their iPhones.
Yeah.
So
people like to back a winner, don't they? And
yeah.
So he was making a presentation there, and I think he wanted to convince people that iPhones were the best thing in the world, best smartphones in the world. And he just hoped they wouldn't notice the change in the rate of increase towards the end of the last quarter there. Yeah. So that just shows how you've got to be careful. Now, here's a graph published by the American government. And what they wanted to convince the population was that they were giving out lots of benefits, federal welfare, and they were a very generous party, and the people should vote for their party. Okay, and so it was a Republican Party. And the Senate Budget Committee produced these statistics, which said it was actually said that these graphs shows over 100 million people in the US are on benefits, now receiving some form of federal welfare. Now, in small print, and you might find it difficult to read, but it says at the bottom here, the figures include anyone residing in a household in which at least one person received a program benefit. Now, there could be a lot of people living in that household and only one person on benefit. But if there were 5 in the household of adults, they would to draw this graph, they would have counted 5 people on benefit, not 1. So it isn't a lie. It does actually tell you exactly the information on which this data was collected. But when you look at it, it's very misleading, isn't it? And you can't help thinking it was deliberately misleading. And sometimes it's a case of people not understanding the data behind the graph they create. So they actually create a graph which is misleading without realizing it. Or they may create a graph and be deliberately trying to confuse either the people who might vote for them or the people who might buy their product or somebody.
Temba made a comment on the previous graph, but it applies to this one. And he said it's manipulated data. It lacks integrity.
Indeed. But I'm afraid I can't put up my hand and say that the United Kingdom government has got integrity.
No, we're not making a comment on the American government. It's governments in general, unfortunately.
I'm afraid that in general, politicians are not the people with the greatest integrity. And you could do a bit of arguing, you could do a bit of logic here. It doesn't mean to say that if a person is a politician, they don't have integrity.
Absolutely. And the thing is that they'll start off with great integrity, a lot of them. And it's not, but yes, you're going back to the logic, but it's also that it's perspective, and people explain you have to do this, or else the party won't get what we need, and all of this. And it's like, oh, for the sake of the party, in that case, that's all right. So there's so many factors.
We've just had an instance this last week where the Conservatives are a big party in the sense that they're in the lead in our parliament, and a lot of Conservatives were very distressed, and they were people with integrity, because they were saying that the rest of the government, including the Prime Minister, hadn't acted with integrity. So yes, I agree about that, and it's a problem existing around the world. Now, the figures in this example include anyone living in a household. We've said that, and therefore they include far more people than the government can justly claim are on benefit. Not only that, but this is classic in misleading graphs. When you want to show a big increase, you just show the graph near the tops of the bars. So if you drew this bar chart starting lower down, then you would not see such a big, because of the piece of paper or poster it was on the screen, you wouldn't see such a big increase. It would look a much smaller increase. But to make it look a big increase, they actually start the graph pretty near the tops of the bars.
And they've done that here. It's an increase of 10 million, which is not, if they'd include the whole bar, it would have been a very, very small difference there.
Yes, and the whole thing is about the whole total is 100 million. You see, so it's only so it's misleading, and one can't help feeling there was some intention there of being a bit dishonest.
That's a huge proportion of the American population. That's nearly a third of the American population. But it's fake. It's fake. It's actually not all those people. Maybe, yeah.
Indeed.
Wow. No wonder they wanted to dramatize it, because it looks. Wow, I hadn't actually looked at the numbers before. That's extraordinary.
Okay, so now on this last slide, I thought we'd look at it together and think about the different types of mathematical model, because the school maths should have changed a great deal over the last few years, because the use of maths in the world has changed a great deal. When I started teaching, the people were using they weren't even using a calculator like this one, which is a pretty, I don't know whether you can see it, maybe you can, there you go, in front of my face. This one is a pretty old calculator. They were using not calculators with a battery in them, but calculators where you turned handles. And actually people were employed. The first moon landing was successful because a lot of women were doing the calculations themselves, okay, using these mechanical calculators, and it wasn't done by the calculations which landed the first men on the moon and got them back safely, were not done by computers. So maths has changed completely now. It's absolutely of no use whatsoever to be able to do calculations and get the right answer when you leave school, or any other maths for that matter, if you don't understand what you're doing, because in fact machines do all these things so much better than people. So what we should be teaching children about is how to use and apply what they learn in school. Now, when we think about applying mathematics, what we're actually doing is using mathematics to model some context, some situation. Now, on the bottom layer, there's 8 different types of mathematical modeling, and here in this illustration, the bottom layer is deterministic. What it means there is there's no probability involved. For a fixed input, you'll always get the same output, and you can have that split up, but the bottom layer is deterministic. The other half, the top layer, is what we call stochastic. What it means is probability is involved. So at least about half the problems situations that we use mathematics for, there's probability involved. I mean, take weather forecasting, for example. Isn't that something that everybody takes an interest in sometime or other? And often it's very important in relation to your planning for your holiday, or to go on a picnic, or, for flights. You don't let an aircraft take off and fly into a hurricane, So weather forecasting is hugely important, but it's all based on probability. The model is a changing model, minute by minute, hour by hour, but it's a model based on probability. And as indeed the medical experiments like the ones we talked about earlier, all medical experiments, all the developments, new developments in medicine are involve probabilities, you know, the number of cases in which this treatment was successful as a proportion of the whole. And next time when we do this trial, the results might be different. So it's all based on probability. And then also, when you look at this, the back block of 4 is for continuous change, and the front block of 4 is for discrete change. Now, if you take something as simple as your age, my age, we are all growing older every minute. I mean, we're a bit older now than we were when we started this workshop, okay? But if we talk about or collect data on something which depends on age, we make it discrete. Actually, I won't be 82 till my next birthday, okay? So I shall go on saying I'm 81 for a whole year, and then suddenly, overnight, my age will change from one thing to the next, and that applies with everybody. And age, when we bring it into a mathematical context and start to draw graphs, and we group people according to age, we treat it as discrete, although in fact it's continuous. And similarly with, let's talk about the speed at which we drive our cars. Now, if we drive and we break the speed limit, then at that point it matters. And it's an abrupt change between being on the right side of the law and being on the wrong side of the law. But actually, as the car moves forward, it doesn't go from 10 kilometers per hour to 15 kilometers per hour to 20 kilometers per hour. It actually, the speed changes continuously, and having an understanding of whether that change is continuous or discrete is very important. And in drawing graphs in your statistical graphs, also, when the data actually occurs at the point of change, which side of that divide do you put that piece of data? You've got to be very clear about it when you're drawing graphs about which group you're putting these people in, if they actually belong on on the borderline. So this idea about in your math, and there's all sorts of mathematical models that are discrete and they're important, and there's also a lot of mathematical models that are continuous and they're important. We haven't talked about left and right yet. So we haven't talked about the difference between static and dynamic. But when I did physics and applied mathematics, we had a subject that was called statics and another subject that was called dynamics. Okay, and statics was all about forces balancing each other and tensions in structures, and about the strength of structures and buildings and balancing, but that was not moving, whereas dynamics was about rates of change and speeds and things that were moving. And so a system which your description works one point at a time is static, and where the system, where it changes in time and it's constantly changing, that is dynamic. So we've got all these different sorts of models, and this is not something you would necessarily present to a class if you were a teacher, but I think what the children need to do is to learn, and it's so important that they do learn, that maths is all about applying it, using what you learn, being able to actually take some information and build a model and reason and work with that model. And that is the nature of being a mathematician these days. That's what it's all about. That's what our subject is about. And it has changed. And it has changed since a lot of teachers started teaching. And they are, and the governments have really got to come up with the right sorts of exam syllabuses and the right sorts of test questions. Otherwise, the employers are going to be saying, these children who leave school haven't got the right skills. They haven't learned to reason. They haven't learned to apply what they know. They don't even really understand it. So just getting, I often say this, and people must be bored of hearing me say it, it's not good enough to get a right answer. In fact, it's not good enough to get all your answers right, unless you can use and apply the maths, what you've learned. So yes, you've got to know that your model fits the specifications, and which of these types of model it's all about. We have got some links for you. The book, it's called Field Guide to Lies and Statistics. Well, I do recommend it. It says that this author is actually a neuroscientist. He's not a statistician or a mathematician. And he's written best-selling books. In this one, it's explaining and debunking statistics in the information age. We live in a world of information overload, it says. Facts and figures are absolutely everything at our fingertip. And they're all around us, and they're too often biased, distorted, or outright lies. From unemployment figures to voting polls, IQ tests, divorce rates, and so on. We're bombarded by these statistics, and we have to be very careful that we're not hoodwinked. This is an eye-opening, entertaining, and accessible guide filled with fascinating examples, and I can recommend it. There's a couple of, there's one reference there to, for the Simpsons Paradox, to some examples on the web there. I can recommend that to you as well.
This is a Global Teacher Empowerment Network video collaborating with AIMSEC and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.